What's up, guys, and welcome to another chapter of system design. Today, we are going to discuss about the Instagram newsfeed. When you open your phone and open Instagram or Facebook or LinkedIn, what is the first thing you see? A stream of posts, stories, reels from people you follow. It looks simple, right? You scroll, you refresh, and then you get more content. But behind that simple experience is one of the most complex distributed systems ever built. I'm talking about a system that serves 500 million users every single day. A system that makes real time decisions about what content to show you out of millions of posts published every hour. A system that has to load in under 200 milliseconds, no matter where you are in the world. Today, we are going to design that system from scratch. We will go through the functional requirement and non-functional requirements, then capacity estimation, we'll do API design and data models, and then we will go deep into one of the most interesting components, like the fan-out models, the ML ranking pipelines, sharded counters, and the celebrity problem. By the end of this video, you will be able to walk into any system design interview and nail the newsfeed question. Now let's get into it. First, let's agree on what this system actually does. What are the things a user can do? Number one, user can publish content like text posts, images, and videos. Number two, users can follow others users. This is a social graph. Then number three is users can see a personalized feed, a stream of posts from people they follow. Number four is users can engage, they can like, comment, and do shares. Number five, the feed should support the infinite scroll, the cursor-based pagination. Then sixth is the real-time updates. When someone you follow posts something, it should appear in your feed within seconds without you having to refresh. Number seven is the content types. It can carry various type of posts, stories, ads, recommendation. The system needs to handle all of this. Now, this is the functional surface area we are designing for. Keep this in mind. Everything we build has to serve these requirements. Now, let's talk about the scale and the quality constraints. In scalability, we need to handle billions of feed requests per day. In availability, this system needs to be about 99.99% of the time. This is less than 1 hour of downtime per year. Then latency, the feed must load within 200 milliseconds. This is the number of users feel. Cross this and the engagement drops. Now the freshness. The new post from the people you follow should appear in your feed within seconds. The most engaging content for you should be ranked higher. And here is a critical one, read to write ratio. The system is a read heavy. For every post you create, there are roughly 100 post feeds that are read. This asymmetry shapes every design decision we make here. About the consistency model. Here, we can accept the eventual consistency. If your friend's post takes around 5 seconds to appear in your feed, that is fine. Nobody is making a financial transaction here. Now, let's put some numbers on this. For the daily active users, we'll be having around 500 million users. The number of posts per day will be around 100 millions. Average friends and follow per user is 500. The feed reads per user per day can be 10. Average post size is about 1 kilobyte. Now let's compute feed read QPS. 500 million users, 10 reads per day divided by 86,400 seconds in a day. That gives us about 58,000 QPS on average. In peak, we can do a 3 or 4 time. So we are looking for around 200,000 QPS at peak. Now the write QPS for post, 100 million posts per day. This divided by 86,400 seconds, about 1200 QPS for writes, much lower than the reads. Now here is the scary number, the fan-out deliveries per day. 100 million posts times 500 followers on average, that is 50 billion fan-out deliveries per day. Let that sink in. Every time someone publishes a post, the system needs to push that post to the feed of every person they are following. 50 billion operations per day. That is why the news feed is very hard. All right, so before we jump into the architecture, let's nail the API. This will be the base on which we'll be making the high-level design. So the core API points are get feed. It gets my personalized feed, takes a cursor for pagination and a limit. The post, it creates a new post, takes a content and media IDs. The post like, it helps to like a specific post. Post follow, it used to follow a user. Now the data model. The post table We will have post ID, user ID, and few of them. I won't go through detail in all of the fields, but you get it, right? Then we will have our social graph table, which will have the follower ID and followee ID and the affinity score and created ad. Now, the affinity score is interesting over here. We will come back to it when we talk about the ranking. For the feed cache in Redis, the structure is a sorted set. The key, feed colon user ID, score timestamp, member post ID, max size 1000 item per user. TTL is 7 days for this one. After 7 days of inactivity, we rebuild the feed from scratch. Why do we need a sorted list? Now you must be wondering, why do we need a sorted set in Redis? Because the insertion is around order of log n. The reads are of order of log n plus the result side. It is perfect for a timeline ordered data. Now the high level design. Let's look at the high level architecture. On the left, we have a user. They go through a load balancer to the main entry points on the write path and the read path. Write path is the post service, read path is the feed service. When a user creates a post, the post service writes to the post DB. It immediately returns a 201 created to the user and does a async everything else. It publishes a post created event into the Kafka. The fan out service consumes from the Kafka. It talks to the social graph service to get the follower list. For each follower, it writes the post ID into their feed cache in the Redis. When a user reads the feed service reads from the Redis feed cache. It calls the ranking service to rank the candidate. Then it merges in celebrity post via pull. It calls the ad service for ad and returns the final paginated feed. This is the skeleton. Now let's go deep into each of the piece. Fan out model is the most important design decision in the entire system. Now, how do we get a post from a user's account into the feed of all the users? There are three models: push, pull, and hybrid. Let's go through each of them. The first model is the push model, also called the fan out on write. When a user creates a post, it immediately pushes it to all the followers' feed cache. The advantage is feed reads are instant. The cache is pre-computed. Just read from the Redis. The disadvantage is writing can be very expensive. If a user has 5 million followers, we need to do 5 million cache writes every time they post. Think about a celebrity like Beyonce, Cristiano Ronaldo, or Barack Obama. They have hundreds of millions of followers. Every single post they publish would require hundreds of millions of cache writes. Now, this is a celebrity problem. The second model is the pull model, also called the fan out on read. When a user creates a post, we just store it in their own post list. When someone reads their feed, we pull the latest post from all the people they follow, merge them, and sort them. The advantage is writes are fast, just 1 dB insert. And the disadvantage is reads are slow. If you follow 500 people, we need to do 500 queries. This is a merge sort, and this is order of n queries on every feed read. At 200,000 feeds reads per second, this is not viable. Then comes the model 3, the hybrid model. This is what Facebook, Instagram, and LinkedIn actually use. The idea is simple. For normal users, we push. We fan out their posts to the followers' caches at the right time. For celebrity, anyone above a follower threshold, say 1 million, do not push. Store their post separately, pull them at read time. At feed read time, we read the pre-computed push feed from the Redis cache and then query the celebrity post list for anyone you follow above the threshold. Then we merge both the list and then rank them and return it. Now, this gives you fast read for the common case and it avoids the fan out storm for celebrity accounts. Now, one more nuance of fan out is we skip the inactive users in the fan out step. If a user has not opened the app in 30 days, we do not bother pushing their feed to the cache. We rebuild their feed lazily when they come back. This dramatically reduces the number of cache writes. The next component we are going to deep dive is the feed generation pipeline. Let's walk through that exactly what happens when you open your feed. Step 1, your app calls the get feed with a cursor. The feed service receives this. Then step 2, it reads your pre-computed feed. This gives us around 100 post IDs. Then step 3 is The feed service queries the social graph to find which celebrities you follow. Step 4, it fetches the recent posts from those celebrity caches. And step 5 is merging them. Now we have around 150 candidates. In the step 6, we batch fetch the full post objects from the post DB. We only stored post IDs in the Redis to save memory. Now we hydrate them. Then step 7 is send candidates to the ranking service. And step 8 is ranking service returns the top 50 rank posts. After that, we go to step 9 where we call the ad server, insert ads at the position 3, 8 and 15. And in step 10, we return 20 posts to the client with a cursor for the next page. The whole thing needs to complete it under 200 milliseconds. Redis reads are some milliseconds, the batch DB reads are maybe 20 to 30 milliseconds, and ranking is the expensive part. We target it under 50 milliseconds. The rest is a network overhead and serialization. All right, now we move to the next component, which is very interesting. Do you know why do we need ML ranking? Because chronological is not enough nowadays. You follow 500 people, they collectively publish 200 posts per day, and then you scroll for 5 minutes. You may see just 15 to 20 posts, but which 15 to see? Now, this is the prediction problem. We want to show you the posts you are most likely to engage with. The features we use fall into these 4 categories. User features. This includes the age, location, interest, past engagement patterns. What type of content do you tend to like? What do you typically like or scroll? Then the post features. The type of post, image, video, text, age of the post, author's engagement history, and the content quality signals. Then the next is the context features. The time of the day, device type, depth into the session. You behave differently on your first scroll versus your 20th post. Then we have the social features. We talk about the affinity scores between you and your author, then the mutual friends, your historical interaction with this author. The model predicts 4 probabilities: P for like, P for comment, P for share, and P for click. The score equals to the sum of the weight times probability of each action multiplied by the content quality score and a diversity factor. Now, why diversity? Because we do not want to show 5 consecutive posts from the same person or 5 consecutive videos. The ranking service runs the inference in under 50 milliseconds, and we use the GPU servers for this. And we cache feature vector for users between these requests. Facebook calls this edge rank. Instagram uses a similar approach. LinkedIn calls there the feed relevance score. The specific weights are different, but the structure is typically same. Now we are going to deep dive into the social graph and the sharded counters. These are the 2 more components worth deep diving. The first is the social graph storage. The social graph is a directed graph. You follow someone, they may or may not follow you back. At 500 million users with an average of 500 connections each, we have 250 billion edges. We store this as an adjacency list in Cassandra. The row key is user ID and the columns is the list of follower IDs or the followee IDs. Now, why Cassandra? Because it is optimized for wide row reads. Getting all 500 followers for a user is a single row scan. We are also maintaining the reverse mapping. Given a followee, give me all the followers. This is what a fan out service needs. We partition this by the user ID. For celebrities with tens of millions of followers, we store the list in chunks with paging. The second is the sharded counters for likes and comments. Now, this is a classic problem. Suppose a celebrity post gets 10 million likes in an hour. Now, this is nearly 3,000 likes increments per second in a single row. Now, if you have a single counter, this is a hotkey problem. Every increment hits the same row. You get right contention and the lock weight. The solution is a sharded counter. Instead of one counter, maintain n counters. Each shard is a separate row. When a like happens, we randomly pick one of the n shards and increment it. When you want the total like count, you sum all the n shards. This distributes the write load across n servers, and for n equals 100, you handle 100 times the write throughput. We keep the sharded counters in Redis for speed and we periodically flush the aggregated counts to the post DB. All right. Then we come to the real-time updates and the notification. The feed auto post you open on Instagram or the new post which appears at the top. How does this work? We have two options. Option one is the short polling. The client polls the server every second. Simple, but it's very wasteful. Thousands of empty requests there can be. Then option two is the server sent events or the WebSocket. For news feeds, server sent events is the right choice. SSC is one-way channel. The server pushes events. The client does not need to send the data back. It works over plain HTTP. Easy to scale with load balancer. When a new post is fan outed to your feed cache, we publish a notification event. Your SSC connection receives it then. The app shows the new post available banner at the top of your feed. You tap it and the app fetches the new feeds. Now, why not WebSockets here? WebSockets are bidirectional, great for chat. Now, for feed that only pushes from server to the client, SSC is a simpler and more scalable. WebSockets require stateful connection, more complex load balancing with sticky sessions or a central connection store. Okay, so here we come to the observability and monitoring. It's very important. Without this, you cannot judge how the system will perform. So a system this complex needs serious observability. Key metrics we instrument are feed load latency, P50, P95, P99 broken down by the component. If P99 spikes, we know where to look. Now, fan out lag, it tells about how many seconds between a post being created and appearing in your followers' caches. Alert if this exceeds more than 30 seconds. Then we do the cache hit rate. This tells what percentage of feed reads come from the Redis versus falling back to the DB. Alert if this drop below 90%. After that, we have Kafka consumer lag. Is the fan out service keeping up with the message queue? If the lag grows, we need more consumer workers. The ranking service SLA P99 of the ranking inference. Alert if it exceeds 100 milliseconds. Now for distributed tracing, we propagate the trace IDs across all the service. When a user reports a slow feed, we can trace the entire request across the post service, the fan out, ranking, and the ad server. Error budgets, we should error budgets by the tier. Feed availability should be 99.99%. This is our SLO, that is service level objective. Then the feed freshness, it should be 95% of posts appears in followers' feeds within the 10 seconds. Ranking fallback rate, this should be less than 1% of the feed requests fall back to the chronological order. Okay, so some of the principal level or staff level engineer questions that you can think about is, they can ask you, what happens during a fan out storm. You can deep dive into how do you handle a misranked feed. Then you can also talk about you store 1000 post ID per user in the feed cache. How do you prevent popular posts from dominating? Then we can talk about how do you handle the cold start problem for the new users. And then what is your approach to content moderation in the feed pipeline? All right, so let's recap everything we built today. We start with the requirements. A system of 500 million users and 200,000 QPS at peak. 200 millisecond feed load latency. We designed the fan-out architecture, push for normal user, pull for celebrities, and then hybrid in production. We built the feed generation pipeline. Redis sorted set for pre-computed feeds. The candidates merging, ML ranking at inference time. We covered Sharded Counter for high throughput likes, Cassandra for social graph storage, Kafka for fan-out feeds. We talked about the observability, latency matrix, fan-out lag, cache hit rates, and we asked about the hard principal engineer questions, the fan-out storms, the model bugs, the content moderation, and cold start. The newsfeed is not one system. It is 5 systems working together. The fan-out, ranking, serving, notification, observability. Master each of this subsystem and you can design any social media platform at scale. Now, if this was useful, like this video and subscribe to Yotamon. Till then, see you in the next class.